Imagine I asked you to look at this and said, what does that mean? Now your inclination might be to say, well, it means 4 times 5. That would not be the correct answer, however. 4 times 5 is what it says. But my question was, what does it mean? This symbol in the middle is absolutely the times sign. And this does absolutely say 4 times 5. But when we talk about 4 times 5 or anything times anything else, what do we actually mean? And to drill down to what it means, we can replace this times sign with a couple of words. We can think way back to realistically primary school, and we can replace this times with a pair of words that really describes what is going on here and what we mean. And those two words are lots of. And what this actually means is 4 lots of 5. The times sign is a quick way of writing that because it's helpful to have a symbol for these kind of things, but really what we're talking about is lots of. 4 lots of 5, as in a 5 and another 5 and another one and another one. A 5, a 5, a 5 and a 5. 4 lots of 5. A 5, a 5, a 5 and a 5. 1, 2, 3, 4 lots of 5. But we could do something else with that, because if we've got 4 lots of 5, well, there are some numbers. We could talk about how many we've got all together. We could talk about what we've got in total. 5 and a 5 and a 5 and a 5. Well, that's 20 in total, isn't it? So therefore, 4 times 5, 4 lots of 5 must be 20. But what we've actually done to get that is we have done 5, added to the second 5, and then we've added on the third 5, and then we've added on the fourth 5. We've done 5 plus 5 plus 5 plus 5 to collect, to group those 4 lots of 5 together. And we've got 20. So really, what does that mean? It means 4 times 5. It means 4 lots of 5. It means get a 5 and another 5 and another 5 and another 5 and add them together and tell me what's there in total. It means keep adding 5s until we've got 4 of them that we're adding together. Other interesting things we could think about here. What if I had not 4 lots of 5, but 5 lots of 4? Well, by the same reasoning, that would be a 4 and a 4 and a 4 and a 4 and a 4. 1, 2, 3, 4, 5 of them, and we'd effectively be adding them together. And if we did that, we would find that we also had 20. And that's interesting, that 4 lots of 5 and 5 lots of 4 both give us the same answer. It's the same amount of stuff, just grouped differently. But the key takeaway of all of that is that this symbol in the middle, it does mean times, it does mean lots of, and it also means effectively repeatedly add up. Timesing is just repeated addition. It's just adding on copies of the same thing until you've got a certain number of them in total. 4 lots, 5 lots, whatever. All timesing is, at its most basic, is repeatedly adding up. And that is a useful thing to recognise. Is that going to be practical all the way through for any old timesing question? Because ultimately that's what we're going to be building towards. Possibly not, but it does mean that when we are timesing, we can just do a bit of counting. We can do timesing as repeated addition. So your first top tip for timesing, if you had something like, say, well, any question really. Something like this, say. You could just do 5 and then add on another 5 and then add on another 5 and add on another 5 and so on until you got to the right number. So you could go 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. Repeated addition, not very useful maybe if the numbers are very big, but it could be useful in some cases. In particular, we could combine it with our second top tip. Our second top tip, imagine we had a question like this, 19 times 4. Now we could do that in the same way, 19 lots of 4, we could do 4 plus 4 plus 4 plus 4 plus 4, count up in 4s and do it that way. Or, with our second top tip, we can think back to what we've just said about the 4 times 5 and the 5 times 4. When we had 4 lots of 5 and 5 lots of 4, they both gave us the same answer. Because it turns out we can do this for any times question at all. We can switch the order and it still works. So instead of doing 19 lots of 4, we could get the same result from doing 4 lots of 19. And that we could do, because we could do 19. We could add on 19, get a total for that, then add on another 19, and then add on another 19, and we'd get to an answer. So there's our second top tip. Switch the order. If you don't like the order they're in, switch the order, make it a bit easier. Maybe it's a number that you're happier dealing with. Maybe it means you could, if you're adding up stuff, add up quicker because you're adding a bigger number. Now, any discussion of times is inevitably going to be followed by a discussion of times tables. And let's be honest, nobody really likes times tables. Now, there will be some of you sitting there thinking, yeah, times tables are fine, I know my times tables confidently. There will be some of you sitting there thinking, yeah, I'm all right on some of them, maybe not so much on others, but, you know, the main ones, the important ones, the ones we use fairly regularly in life, I could probably have a good go at. I might have to count up. I might not know them all necessarily straight off the top of my head, but I could probably count up, maybe write them down. I know them reasonably enough. And there will be some of you sitting there not knowing their times tables. Now, there is a common thinking that you must know your times tables, that everybody has to know them, everybody needs to know them by heart, so I could throw a question at you and you could immediately tell me the answer. And it's just rubbish. Between you and me, you don't really need to know your times tables that well. It's helpful if you know them. It is. I'm not going to pretend it's not. The difference between you knowing your times tables really, really well and you knowing them a little bit, maybe you've got to count up, maybe you'd have to work something out individually. The difference between you knowing them really well and not is that in a question, you're doing a big question, it's not a times question, but at some point in the question you come across a simple times table question, something like 6 times 7. If you know your times tables, you get to that step, you go 6 times 7, you immediately write down the answer, it's 42, done. And you move on to the next step. If you don't know your times tables, you get to that step, you look at 6 times 7. And then you think, right, okay, 6 times 7, so we're going to go 7, 14, 21, 28, 35, 42, right. And then you carry on with the question. Maybe you've written something down, maybe you've worked it out, whatever. However you got there, you've got there. And that's the difference. If you know them, great. You come to that bit in the question, you whiz past it. If you don't know them, not that big a deal. You just have to sit there and work it out. It slows you down slightly maybe, but it's not going to have that much of an impact. If you want to go away and learn your times tables, please by all means do. But if you don't, if you know in your heart of hearts that you are not the kind of person who could sit and learn the times tables and would actually be better off just working them out when you get to those kind of bits, fine. But if you are going to go and learn them, I would suggest you maybe focus on certain ones as being slightly more important than the others. The most useful times tables are probably 2, 5 and 10, because they are the ones that are arguably easiest to look at, and they are the ones that are probably going to be most useful to be able to do quickly. The idea of being able to say 1 lot of 2 is 2, and 2 lots of 2 is 4, and 3 lots of 2 is 6, and 4 lots of 2 is 8, and so on. 5s, 1 5 is 5, 2 5s are 10, 3 lots of 5s are 15, and so on, and 10s, 10, 20, 30, 40, 50, and so on. How you do this is up to you. First thing, it's worth recognising that there is a pattern here. If we look at the answers here, 2, 4, 6, 8, 10, and so on, we are going up by 2 each time. Now that makes sense because the times tables, the 2 times table is just a list of the numbers going up in 2 from 1 lot of 2 to however many. Notice that in all these cases we've only gone as far as 12 because that's generally enough if you're going to learn them. Anything more than that you'd probably just want to work out. There's no real need to know what 13 or 14 or whatever lots is. You'd probably just work those out. And you can always count on from 12 anyway. If you know what 12 lots of something is, 13 lots is just another lot of it. The 2 times table in particular, it makes sense that it will be going up in 2s. 5 lots of 2 to 6 lots of 2, for example, is an extra lot of 2, so the answer will go from 10 to 12, an extra lot of 2. 5 times table goes up in 5s for the same reason, and the 10 times table goes up in 10s for the same reason. These are the 3 that you're probably going to want to focus on. You might also want to notice that there are certain patterns in these. The 5 times table, 5, 10, 15, 20, 25, 30, and so on, all end in a 5 or a 0. Makes sense if you think about it. And the 10 times table all end in a 0 because they are all going to be tens numbers. Yes, okay, we get to 100, 110, 120 at some point because we've crossed into that hundreds thing, but think about the hundreds, tens and units and how it's all based around tens type things. We talked about this idea of base 10, for example. 10, 20, 30 all ending in a 0 because they're all tens numbers. If you wanted to learn a couple more times tables, you could do worse than looking at the 3s, the 4s and the 9s. They are also quite useful times tables and there are interesting things to notice in there. The 3 times table going up in 3s, the 4 times table going up in 4s. The 4 times table, notice that all of these numbers in here would also turn up in the 2 times table. That makes sense because 4 is just 2 lots of 2. The 9 times table, if we ignore just these last 2 for the minute, and if we treat this as being, rather than just a 9, but a 0, 9, as in no tens, just to make this work, you might notice that if we look at the tens numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, increasing digits, and then on the other side, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Nothing fancy to that, it's just a quirk of the number system. It works because it works, but it is an interesting pattern, and if you're the kind of person who likes patterns and responds to patterns, it might be something worth noticing. There is a neat trick that can be done with the 9 times table. This only works with the 9 times table, and it's just a quirk of the number system again. You get your 10 fingers like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So running from 1 to 10 in that order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Imagine we wanted to work out a 9 times table question. Let's say we want to work out 4 9s. 4 lots of 9. So I'm going to put down my 4th finger. 1, 2, 3, 4. I'm going to put this finger down because I'm working out 4 9s. How many fingers are there on this side? On the left of my 4th finger. 1, 2, 3. How many are there on the right side? 1, 2, 3, 4, 5, 6. And 4 9s are 3, 6. 4 9s are 36. We'll do another one. Let's say I wanted to work out 8 9s. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to put down my 8th finger because I want to work out 8 9s. How many fingers are there on the left of my 8th finger? 1, 2, 3, 4, 5, 6, 7. And how many on the right? 1, 2. And 8 9s are 72. Again, it only works with the 9s, but it is something that you could do to work out the 9 times table if you wanted. If you were learning times tables and the others were going well, you could even go that final step and learn 6, 7, 8, 11 and 12 times tables. Nothing really to notice about these other than to say that the 7s is probably the hardest times table to recognise because there really isn't a pattern with those. The 11s is probably one of the easiest because there is a nice pattern. 11, 22, 33, 44, 55, 66, 77, 88, 99, and I'm going to let you work out what the pattern there is for yourself. How would you go about learning your times tables if you were going to? Well, there's a couple of different ways. You could just learn them as a bit of a chant. It's quite an old-fashioned thing to do, I suppose, but learning them by rote, it's the only bit of maths I would ever suggest you do learn by rote. Learning them as a chant, 1, 2 is 2, 2, 2 is a 4, 3, 2 is a 6, 4, 2 is a 8, and so on, does work. And you can kind of train your brain to recite that. Equally, you could just learn the answers, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and so on. You could get somebody to test you on them. You could get somebody to fire random times tables at you and you have to respond quickly. It depends how you want to do it if you are going to learn them. But again, there is no necessary need to do it. If you are more comfortable just working them out as and when you come to them, then do that. Although you will find that some of the more useful ones, particularly things like 2, 5 and 10, will start to sink in anyway. It is possible that that way of presenting the times tables as lists is not going to be one that you particularly click with. You might prefer to use a times table grid, where we have numbers 1 to 12 across the top and the numbers 1 to 12 down the side. If you wanted to work out a times question, for example, you would find one half of the sum along the top and one half of the sum along the side. If we wanted to work out something like, well, we'll do 6 sevens because we've already found the answer to 6 sevens earlier in the video, you would find the 6 on here and the 7 on here, and you're going to look for the square where the row and column meet. So we're going to go down the 7s until we hit row 6, and across the 6s until we hit column 7, and 6 sevens are 42. Underneath the 7 across from the 6, 42. Notice that is in fact the same as if we did 7 sixes. We're across from the 7 and down from the 6 because 6 sevens and 7 sixes are the same. So actually this grid is symmetrical about here. It is the same either side of this diagonal because of this repeat thing. If you prefer to use a timesing grid, it's not that practical because you couldn't use it in an exam, but certainly while you're trying to get to grips with them, if you are learning them, using one of these might work. You could use it as a reference. This one only goes up to 12 by 12, but you could always produce your own that go further if you wanted to. Again, we don't tend to need to know much more than 12 times 12, but if you wanted to have bigger numbers on there, you could do. Anything bigger than 12 times 12, we probably just work out using one of the methods that we're going to come to later. Now there's a common line of thinking that says when we're doing something like this, 7 times 10, when we're timesing by 10, we just add a 0 on the end, surely. And 7 times 10 will be 7 with a 0 stuck on the end, and be 70. Fair enough, seems reasonable enough. 7 times 10 is 70, it's 7 lots of 10, 10, 20, 30, 40, 50, 60, 70. Perfectly fine. If that is true though, then we could take a question like this, 4.5 times 10. When we times by 10, we just stick a 0 on the end, don't we? So that would be 4.5 with a 0 stuck on the end. And hopefully you notice something weird about that. Because 4.5 and 4.50, think back to the place value stuff. 4 in the units and 4 in the units. 5 in the tenths and 5 in the tenths. A 0 in the hundredths and nothing after here, but if we wrote them in the grid, there would be a 0 in the hundredths. And by this reasoning, this stick a 0 on the end if you times by 10, 4.5 times 10 would be the same thing. And if you are timesing something by 10, it will get 10 times bigger. It will not stay as it is, which means that this is wrong. And it means that the whole stick a 0 on the end of it thing doesn't really work. So maybe we need a better way of thinking about timesing by 10. Consider the hundreds, tens and units grid. Imagine I put a number here in the units and I put a 7 in there. That is clearly a 7. Now if I were to move that 7 into the tens, put a 7 in the tens instead, its place value has clearly got bigger. We also know that it's not a 7 anymore, it's a 7 tens or a 7t. And really, to make that a proper number, we can't have random gaps in numbers. We have to make sure we've filled the grid up to the decimal point from either side. Then it is complete. So we can put a 0 in the units to make it a 7t. Now in doing that, in making that move, the 7 has got bigger. It's become a 70. It has clearly got bigger. In fact, going from a 7 to a 70, its place value has changed, its place value has increased, and the number itself has physically got bigger. In fact, it has got 10 times bigger, and there's a key thing in what I've said there, it's got 10 times bigger. So what we've done really in moving the 7 up here is we've made it 10 times bigger, we have timesed it by 10. Imagine now that I move the 7 once more and put it in the hundreds. It's now a 7 in the hundreds, it's a 700. In fact, we can fill the number out again. We can fill in those 2 extra columns to make it a proper number, a 700, because we can't have random gaps in numbers. The 7 has moved one more place. It has moved from tens to hundreds. It has moved from 70 to 700. It has got 10 times bigger again. And in fact, if we look at how the 7 has got bigger from 7 to 700 rather than just 70 to 700, overall it's gone from 7 to 700, it must have got 100 times bigger. Which makes sense because it's got 10 times bigger, then 10 times bigger again. And if you want to think back to your times tables that maybe you started learning or not, 10 times 10 is 100. It's got 100 times bigger. Now we can use this hundreds, tens and units to our advantage in this way. We can think about numbers getting bigger on the grid. In fact, it turns out that every column, it has to work this way because otherwise the grid falls apart. Every column is 10 times bigger than the previous one. How is that useful? And why is that useful? Well, because if we take a number and we shift it one column up in the grid, then what we've done is we've timesed it by 10. We've made it 10 times bigger, so we must have timesed it by 10. If we move it 2 columns up, we've made it 10 times bigger and 10 times bigger again. We've made it 100 times bigger. If we move it 3 columns up, we've made it 10 times bigger, then 10 times bigger, then 10 times bigger again, and 10 times 10 times 10, 1000. So just by moving stuff around in the grid, we can make stuff 10 times bigger, 100 times bigger, 1,000 times bigger, 10,000 times bigger if we wanted, 100,000 times bigger. We just need to know how many columns we're moving things up by. So the key thing is this doesn't just work with single digit numbers. 18 times 10. We'll put the 18 where it needs to go. 1 in the tens, 8 in the units. We're timesing by 10. Now first thing, we're timesing. We're making the number bigger. It's going to move up the columns. It's going to move this way. We're going by 10. How many jumps does that go? Well, each column move is 10 times bigger. So what's going to happen is each of these numbers are going to get 10 times bigger. The 1 in the tens is going to get 10 times bigger and it's going to move into the hundreds. The 8 in the units is also going to get 10 times bigger and it's going to move into the tens. It's going to move 1 jump each. Is that a complete number? Well, no, it isn't, because we have to fill our grid up to the decimal point. So I need to add something to this number to make it a complete number. I need to show how many units there are. And how many units are there? Well, none. The only extra information I can add when I'm doing this kind of thing is zeros. And I only need to add as many as I need to make the number complete. 4.56 times 100. We're going to make the 4.56 100 times bigger. If we're timesing, we are moving up the grid that way. We're making it bigger. Everything's going to get bigger in place value. Lots of something, it will generally get bigger. we're going by 100. 10 is 1 jump, so 100 is 2 jumps. I'm going to put the 4.56 in where it goes. The decimal point will help me line things up. 4 in the units, 5 in the tenths, 6 in the hundredths, and that decimal point underneath the decimal point in my grid. We're going by 100. So each of these numbers is going to move 2 jumps up the grid. So the 4 is going to start in the units. It's going to move 1 jump into the tens, 2 into the hundreds, and it's going to end up there. 4 in the hundreds. The 5 is going to cross this decimal point and move into the units, and then move another jump into the tens. The 6 is going to move into the tenths, and then it's going to jump across the decimal point and end up here in the units. 456, 456. Is that a complete number? Well, actually, in this case, yes, it is. We've filled up to the decimal point. There is no need to add anything else because that is a complete number. Does that make sense as an answer? Well, let's just check this question. 4.56 times 100. If I ignore the 0.56 and think, well, that's something that's around about 4 lots of 100 would be 400. So that sort of makes sense as an answer. It's around about the right kind of size. But we've used the hundreds, tens and units grid to help us. Notice as well that the digits in the answer are the same as the digits in the question. It's a 4, a 5 and a 6 in that order. We've not lost any digits, we've not gained any digits. The only thing that we might have added in, if we needed to, would be a 0. In this case we haven't needed to because the number is complete. But the 4, the 5 and the 6 are still all there, and they are in the same order. 4, then 5, then 6. It's almost as if the 4 has moved 2 columns up and then dragged the 5 and the 6 with it. You don't necessarily have to move each number individually, although you can do. Now, if moving this way in the grid is timesing, because we're making things bigger, it makes sense that going down the column, starting from a column here and moving down to the 100,000s, down to the 10,000s, thousands, hundreds, tens, units, and then down to the tenths, the hundredths, the thousandths, it makes sense that things will be getting smaller. In fact, every jump would be 10 times smaller. If they're 10 times bigger, moving towards the left, moving things down the grid would make it 10 times smaller each time. Now we need a way of showing that 10 times smaller. And this is a little bit of a hand-wavy thing for the moment. We'll explain this symbol more properly later on. But if we're making things smaller, we're cutting them up into chunks maybe, making them smaller. We are, in fact, dividing. The opposite of timesing. And again, I appreciate we haven't talked about dividing yet. All that will come very soon, don't worry. We will address this symbol a little bit more carefully and we will define it a little bit more carefully. But if timesing is making things bigger because we've got lots of something, dividing will make things smaller because of that sharing process that we'll talk about soon. So each time we move down a column, we are dividing by 10. Now that means that if we are going 1 jump for 10, 2 jumps for 100, 3 jumps for 1,000 when we're timesing, the same is going to be true for dividing. 1 jump down for 10, 2 jumps down for 100, 3 jumps down for 1,000. Might be worth at this point trying to notice a useful pattern there. 1 jump for 10, 2 jumps for 100, 3 jumps for 1,000. What about the numbers might clue us into that? If, for example, we could remember it was jumps, but not how many. Look at the numbers 10, 100, 1,000. What clue is there in the numbers to tell us how many jumps we're going to make? Yes, it's the number of zeros. 1 0 in 10, 1 jump. 2 zeros in 100, 2 jumps. 3 zeros in 1,000, 3 jumps. Up for times, down for divide. (27) divided by 10. We'll start off, we'll put the 27 in the grid where it should go. 2 in the tens, 7 in the units. 27 divided by 10. We're dividing, so we're going down the grid. Timesing is up, dividing is down. We're going by 10. 1, 0, 1 jump. So each of these numbers is going to move 1 column down. 7 is going to move 1 column down. It's going to cross that decimal point and it's going to end up in the tenths. The 2 is going to move 1 column down. It starts in the tens. It's going to end up in the units. It's crossed that decimal point, so we need to put it in. 2.7. Is that a complete number? Well, yes, it is. That's a perfectly reasonable number. We don't need to add anything to that. Anything we added wouldn't change the number. So we don't need to put anything on there. It is a perfectly reasonable number. 4.3 divided by 1,000. So it's getting trickier now, but we can still use all the same patterns as before to help us work this one out. 4.3, we're going to put that in the grid first of all. 4.3, 4 in the units and the 3 in the tenths, that decimal point in the middle lining up with the 1 in the grid. We are dividing, so we are going down the grid. We're making things smaller in value because we're dividing, bigger in value for timesing, up the grid, down the grid for dividing, making things smaller in value. We're going by 1,000. 1,000 has 3 zeros. There's our reminder. 1 jump for 10, 2 for 100, 3 jumps for 1,000, 3 jumps, 3 zeros. Each of these digits then is going to move down the grid. 3 jumps. So the 3 is going to start in the tenths. It's going to move 1 jump into the hundredths, 2 into the thousandths, and then, oh, hang on, we've run out of grid. Well, that's okay. There are more columns after here. The 10,000ths column would come afterwards. I'm just going to squash it in at the end because it is still there. It is possible to exist. There is a 10,000ths column there. I could add the column header if I wanted. The 4 is also going to move 3 jumps. It's going to be dragged down by the 3 in the same way. 1, 2, 3 and end up in the thousandths. Is that a complete number? Well, no, far from it. In fact, we'd need to have something in the hundredths, so a 0, something in the tenths, so a 0. We need to have the decimal point in because we've crossed into that decimal section. As soon as we cross into the decimal area, we have to make sure we've got a decimal point in. And just as a style thing, I'm also going to write in a 0 for the units. Whenever we've got point somethings, we always have to have a units number just because it's a bit neater. So I'm going to show that there are no units there and have 0.0043. Tricky decimal perhaps, but because we've just used the hundreds, tens and units grid to help us, we've been able to do that divide. Downside of this sort of stuff is it only really works for 10, 100 and 1,000, and you could adapt it for 10,000, 100,000 and so on. Count the number of zeros to work out how many jumps it would need to go.
Think about this question 10 times 7 again. 10 lots of 7. Let's remind ourselves what that might look like, in particular playing on this lots of idea. Well, there are 10 lots of 7. There's 7 green dots in each of the groups, and there are 10 groups overall, 5 on the top row, 5 on the bottom row. Now, thinking about this 10 lots of 7 as repeated addition, one of the earlier definitions that we took for it, we could count up how many dots there are there in total, and that would be the same as doing 7 plus 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 7. That will be exactly the same as counting up each of the dots individually, or of course of putting the 7 in the hundreds, tens and units grid and moving it up one column for the times by 10. Whichever way we do it, we're going to generate the answer 70. But that's what 10 lots of 7 looks like. Now, there are a couple of other things it's useful for. There are some other multiplications, some other times that we could easily work out from the 10 times 7 without having to do much extra work. We can just use that simple fact that 10 times 7 is 70 to find other things. Consider now instead 5 times 7. What would 5 times 7 look like? Well, here in the picture we have 10 lots of 7, but we're not interested in 10 lots of 7. We're interested in 5 lots of 7. Well, surely 5 lots of 7 is just, for example, the top row. There's also 5 lots of 7 on the bottom row, but we're going to focus on the top row. Well, before we picked out the top row, we had 10 lots of 7, and that was 70. Now, half of the 70 is contained in the 5 circles on the top row, and half is contained in the 5 circles on the bottom row. Well, that means that if 10 lots of 7 is 70, 5 lots of 7 must be half as much. Which means that 5 lots of 7 must be half of 70, and half of 70 is 35. Now, this is true for any number, not just 7, but if we know what 10 lots of something is, 5 lots of that thing must be half as much. There's something else that we could use 10 times 7 for as a basic fact to find other things. Let's consider again the 10 times 7. There is 10 times 7 is 70. Now imagine now we wanted to find 20 times 7 without having to work it out, without having to use some fancy method. Well, 10 times 7 is 70. There it is. Let's put another 10 times 7 there. That's another 10 times 7 is 70. If I want 20 times 7, all I need to do then surely is collect together those two lots of 10 times 7, because the first 10 times 7 will give me a 70, the second 10 times 7 will give me another 70. That's 20 lots altogether. 20 lots altogether, surely I just need to add the two 70s and get that 20 times 7 is 140, which we've worked out from simply one fact, that 10 times 7 is 70, and we've doubled it to find the 20 times. And again, this will work for any number. 10 times a number, halve it to find 5 times, double it to find 20 times. We could go one step further with this as well, and we could think about two of the facts that we've already obtained. We could think, for example, about the 10 times 7 is 70 and the 5 times 7 is 35, and we could start to put these facts together in clever ways. This is particularly good because the 5 times 7 we found from the 10 times 7. So we've only really had to know one fact. There's a second fact that we've then worked out. I could use those two things together to find 15 lots of 7, because there, in the 10 times 7 and the 5 times 7, we have got in total 15 lots of 7. So surely all I need to do to find 15 lots of 7 is take the 70 in the blue box and take the 35 in the yellow box, put them together, add them up, and find that 15 times 7 is 70, plus 35, or 105.
We can even extend this idea and use it to work out other things, besides just using 10 to find 5 and 20, and maybe things like 15. If, for example, we have as a standard fact that 10 times, say, 18 is 180, we might get that from our hundreds, tens and units grid like we did before, for example. We can then work out fairly quickly that 5 times 18 must be half as much. Half of 180, well, half of 18 perhaps would be 9, so half of 180 would be 90. We might also be able to work out, say, that 20 times 18 would be 2 lots of this, 2 lots of the 10 times. 2 lots of 180, we could work that out. We could nip off to the side and add them up maybe in columns. 360. But we could start to put some of these together as well. We could, for example, work out 25 times 18. Well, if we know that 5 times 18 is 90, 20 times 18 is 360, if we put those two things together, we will get 25 times 18, 25 lots, 20 lots here, 5 lots here, 360 plus the 90, 450. If we added another fact, say, something like 2 times 18, well, think about 20 times 18. 20 times 18 is 360. 2 times 18 will be 10 times smaller, because the difference between 2 and 20 is 10 times bigger. So the answer here will be 10 times smaller, and 10 times smaller than this will be 36. The 360 will shift down the columns. Alternatively, 2 times 18, we could just do an 18 plus an 18 and work out 36 that way. Either is fine. But we can start to put these together, because maybe we want 7 times 18. Well, 7 times 18, we could use the 2 times 18 and the 5 times 18. Put those together to get 7 lots. 90 and 36, well, that would be 126. We could even start to put these together in slightly different ways. If we know that 10 times 18 is 180, we could easily work out 9 times 18 without having to work it out using a proper long method maybe. 10 lots of 18 is 180, 9 lots of 18 will be 1 lot less, as in 180 take away an 18. And if we were to do that, we would find 180, well, take away 10 is 170, take away 8, 162. And 9 times 18 is 162. final thing it's worth pointing out when we're talking about timesing is what happens in two very specific cases. And those cases are a number, any number you like, times 1, and a number, any number you like, times 0. Or the opposite way around, 1 times a number and 0 times a number. Because remember, of course, timesing, we can write them either way around and they will give us the same answer. If I take a number, any number you like, 4, 17, 3.2, and you times it by 1, you just have one lot of it, which means you are going to return as an answer the same number. As in, 4 times 1 is 4, 5 times 1 is 5, 1 times 3.2 is 3.2. If I do anything times 1 or 1 times anything, nothing's going to change. The other case worth considering is if we are timesing by 0 or having 0 times something. No lots of something. A number, any number you like, times it by 0, we are having 0 lots of it. And if we have 0 lots of something, we have nothing at all. So any number times 0 is just going to be 0.